Unit 4. I've got the notes loaded into Google Classroom. If you want to follow along on those notes, you may want to print out those notes and use them for tests and assignments. You may want to print those out and fill them in. And we're going to fill in a lot of them during this video, during this class period right here. So let me put it up on our screen so we can all see together what in the world we're doing here. All right. I wore my little pencil out. It's getting very short. I'm going to have to replace that thing. We're working with polynomial functions. So let's talk about polynomial functions. We're going to talk about their characteristics and what's important to know about polynomials. So a polynomial function is a function of this form, f of x equals, and a sub n to the x to the n power plus a n minus 1 x to the n minus 1 power plus a n minus 2. All right, so the coefficients, a sub n minus 1, are real numbers. So this would be like 2x to the third power or something, right? This would be the next coefficient in the next power. N is a positive integer. A sub n cannot equal 0. I mean, we can't have like no function at all because we only do positive numbers, no negative exponents. So a sub n is called the nth term. A sub n would be the nth term. So let's look at these examples and start talking about degrees and leading coefficients of functions. So let's start with this one. We're going to start right with quadratics because we've worked a lot with quadratics. We're very familiar with those. So what degree function is? This is, and to tell what degree function is, you look at the largest exponent, right? For the variable. For the variable, what's the largest exponent? This is an x squared. This is just an x to the first power. So the degree is 2. This is a second degree polynomial. And the leading coefficient is the coefficient for the largest exponent. Since that's the largest exponent, our leading coefficient is a 12. I know we have a negative 11 and we have a 31, but the leading one is the one that goes with the largest term. The largest term. Even if they were out of order, this could be negative 11x plus 12x squared plus 31. 12 is still the leading coefficient. This is just a negative 5x plus 1, so that's a first degree, and the leading coefficient is a negative 5. Right? Negative 5 is what goes with the x. This is actually a 0 degree, and there is a leading coefficient with the x, and it's a 0. That's why the x is not there. The leading coefficient is a 0, so it's a 0 degree polynomial. Here we have a third degree because that's the largest one. Got to the fourth power, to the second power, and just a constant, so that's a fourth degree. And finally, we have a fifth degree. So what is our leading coefficient for our third degree polynomial? It's a negative. It's a negative what? A coefficient's a number. That's negative 1. That's negative 1 x to the third power. Good job. Brianna was on top of that for us. She beat me on that. Coefficient for this fourth degree, the leading coefficient, negative 3. And, of course, a 9. All right, so that's pretty understandable. We just have to check and see what's the largest exponent. If the largest exponent's a 1, or if it doesn't exist, that's only in special cases. Otherwise, just take that largest exponent. All right, so let's look at identifying the parent function and then sketch a graph using your graphing calculator. Or we can do it with Desmos, or since we know what it looks like for most of these, we can just do that. We'll open up Desmos and have that ready just in case. Desmos. All right, it is ready. So a constant. Well, that's just a y equals, and we'll just call it a c for a constant. Like y equals 4, or y equals negative 2, or y equals, that's just a straight line at a number. If y equals 3 is right there, maybe that is what the graph looks like. Right? Whatever. 1, 2, 3. That would be y equals 3. So that's just y equals a constant. Linear, we know what linear looks like. The parent function is just y equals x. Now that could change, mx plus b. We might change that, but the parent function is just y equals x, or f of x equals x instead of y. Let's even write it as an f of x just to stay consistent with functions. F of x equals c, or f of x equals x, and so that's just a line, right? That's just a straight line. That is f of x equals x. It's just 1, 1, 2, 2, 3, 3, 4, 4. That can change depending on whatever transformation to do that. Quadratic is f of x equals x squared. That's our parent function, right? And we know what that looks like. That's just a parabola. Cubic. F of x equals x to the third. And do you know right off what x to the third looks like? I got it. I want to go ahead and put it on here for you, but equals x to the third power. That's what the f of x the third power is. We knew the parabola. Oops. There's the parabola. If we change it to a third power, there's the cubic. So we can kind of draw that. Kind of goes flat just a little bit right through there. So there's what the parent function looks like for a cubic function. All right, let's look at our next page of notes here. Quartic. What is a quartic function? Well, that's x to the fourth, and quintic. Get into the English on what are these prefixes? X to the fifth. So what does an x to the fourth and x to the fifth look like? Well, if we look at it, x to the fourth, we're going to compare it to x squared. Oh. There's x squared. Compare that to x to the fourth. X to the fourth is flatter down here at the bottom. See the blue and how it will zoom in here and see, get a good look at it. I'm going to take out all these extra lines in there and just have it on the ones. So it's flatter than the normal parabola and goes up faster. You see it spends more time really close to zero down there. So we can draw that on our sheet. So it goes up a lot faster, and it's going to be flat along there for a longer period of time than the parabola does. All right, so let's look at the quintic, and we're going to compare that to an x to the third. So if we change this to a third power, and then change this to a fifth power, kind of the same thing. Look at that, how it's flatter, stays closer to zero longer. Now it's not zero, but it's very close to 0, 0.01, 0.02, 0.03, 0.04. Well, this is starting to go down on the red one, starting to go down a lot faster. So it just flattens down more. And if you want to make it extreme, let's make it x to the 15th power and see it gets even more and more. The bigger the exponent, if it's an odd exponent like this, just the more it stays close to 0 for the longer amount of time. So knowing that, we can know that this works a lot like the third, but it comes down and it's a longer period of where it's very close to 0. Close to the third, but it stays flatter longer. Oops. And just like this is the fourth is just flatter longer, but it's kind of like the parabola. So that kind of gives us a visual in our notes of what those look like. All right, so let's look at this. In behavior patterns, that's one thing that we need to know, and we're going to learn to identify this. So we can use our graphing calculator to determine the in behavior. Now let's talk about, I'm going to zoom in here so we can see what this says. All right, now we're focused. For this function, this is as x approaches. Okay, this is the pro. That's usually with that arrow. As that x approaches infinity. as x approaches infinity, which means on a graph, as x is getting bigger, x is closer and closer as it approaches infinity. What does the function do? The function approaches something, right? Like on this one up here, the function is going up. It's approaching infinity, going upwards. It's getting bigger and bigger and bigger. But let's check out for this equation right there. So we're going to type that into Desmos. It says we can use a graphing calculator. So 4x to the fourth plus 6x to the third minus x. Okay, so that's what the graph looks like. So as x approaches infinity, and we can zoom out a little bit here. As x is getting bigger and bigger, what's going on with the function? It's getting bigger and bigger. It's going up. In fact, it's quickly approaching infinity. It's going up very fast. And as x approaches negative infinity, going to left, as we're moving left, we move left on the negative x, what's it doing? Well, it's going up and up and up. The more we go negative x, the bigger that number gets. So both directions, it's approaching infinity. So as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x also approaches infinity. So both ends, the end behavior, it approaches infinity on both ends. All right, let's look at this one. Negative x squared plus x. Negative x squared plus x. Oh, okay. It's a parabola because it's an x squared, so we expected it to be a parabola. And we see both sides, as x is getting bigger, it's going down to negative infinity. As x gets smaller, it's going down to negative infinity. So it doesn't matter which direction we're looking at there. It's going to negative infinity on both ends of the graph. Both ends are going to negative infinity. So let's look at 2x to the third. Number 3 right here, 2x to the third. So we'll kill that out. 2x to the third, right there. Well, it looks a lot like x to the third, like the paragraph. It's just got a 2 multiplied times 2, so all the y's are twice as tall, both directions. So as x goes towards infinity this way, this is going up towards infinity. As x moves towards negative infinity, this one's going down to negative infinity. So x to negative infinity, as x to positive infinity, the graph's going to infinity. X to negative infinity, it's going to negative infinity. So this one works the same as x. It goes to infinity, and as x goes to negative infinity, the function also goes to negative infinity. Negative x to the third. Okay, so let's take off the 2 and just put a negative out there. Oh, look, it turns upside down. Turns upside down. Now, as x is getting larger, the function's getting smaller, going to negative infinity. As x gets smaller, the function's going up to infinity. So this is the opposite. It's an opposite effect on this one. As x approaches infinity, the function's going to negative infinity. And as x approaches negative infinity, we're approaching positive infinity. All right. Last thing we'll do is these two, and then we're going to kind of see if we can come up with a pattern. Negative 2x squared plus 4x, say 2x squared. Negative 2x squared plus 4x plus, minus 7. Minus 7. Gotta zoom out because it's a minus 7. Okay, that's a parabola because we have an x squared, and it's going down on both ends. Negative 2x squared, it's going negative infinity on both ends of the function. Now we have 1/2 x to the third. What does that do to it? 1/2 x to the third. 1/2 x to the to the third plus 7. The plus 7 just brought it up there, but still, it acts just like a regular x to the third. It's just coefficients will change a little bit. If we take out the 1/2, it just straightens it up a little higher. See, it's kind of a vertical compression. But still, as x goes to infinity, this is going to infinity. As it goes to negative infinity, it's going to negative infinity. So this goes the same as x. All right, so looking at those, what do we see? Let's compare even degree and odd separately. So even degree. So which ones are even? This is an even degree because 4 is the largest exponent. This is an even degree. This is an even degree. So those are all even exponents that are the largest degree function. 4th degree function, 2nd degree function, 6th degree function. These two are both negative. This one's positive, right? The leading coefficient. If we have a positive leading coefficient with even degree, we can draw sketches to remember the end behavior patterns. So even degree, only one of these had a positive, but what we saw is both ends, the left end went up and the right end went up. That's what we saw when we had a positive coefficient for an even degree. When we had a negative, this is both even degree, -1 and -2, both of those went down on both ends. The left side went down and the right side went down. How about odd degrees? So these three are all odd. Positive is 2 of them. We have a 2 and a 1/2. Those are both positive. And what did we see? We saw the same thing. As x goes to infinity, it goes to infinity. That's on the right side. When x is going to infinity, the graph is going up, right? And as it goes to negative infinity, as it goes left, both of these are going down to negative infinity. So with an odd degree, with a positive leading coefficient, we see the right end of the graph will go up and the left end will go down. Now, what it does in the middle can vary. It can do all kinds of stuff in the middle, but the very ends of the graph, you're going to see go in that direction. Negative leading coefficient, we had 1, and it did the opposite. As x went to infinity, it went down. When x went to negative infinity, it went up. So this is kind of like our little cheat sheet right here, based on the degree of the function and whether the leading coefficient is positive or negative. Little cheat sheet. So now they give us 2 little graphs down here. It says, determine the sign of the leading coefficient and is it even or odd? Okay, well, so what do we see? We see both going down. So that tells us, according to our little cheat sheet, that's negative leading coefficient and it's even degrees. It's negative and it's even. What do we have here? We have the right side going up, the left side going down. There's only one kind that does that. Right side going up, left side going down. So this is a positive leading coefficient. And it's an odd degree function. Just using our little cheat sheet. Didn't have to put a lot of thought into it. Didn't have to know what the equation was. None of that. Just looking at the end behavior tells us a lot. We already know if it's even or odd. We already know if it's positive or negative coefficient on the leading term. All right. Let's look at something else. Let's look at turning points. Okay, so turning points. So it says a turning point is the point at which a polynomial function switches direction. Well, that makes sense. It's where it switches direction. And if the turning point is higher than any nearby point, like this is a turning point right there, right? And it's higher than both the sides. This point is higher than the points around it, right? That point is higher than any point around it. So that is called a relative maximum. That's a relative maximum, because relative to the things around it, that is the highest point. That's the maximum y value relative to what's around it. Now, it's not the largest y value total, because over here, this is going to infinity. There are y's much bigger. But relatively speaking, just for that area of the graph, it is the maximum value. So relative maximum. If the turning point's lower than any of the nearby points, like right here, this is lower than the points all around it, we have a relative, but you got this one guessed already. Minimum. So maximum and minimum values are called extrema.
Okay, so most bugs do
because it's the extreme maximum value in this area. This is the extreme minimum value. We call it extrema. So turning points define, okay, a lot of people have trouble with this. The turning point defines where the function is increasing and decreasing. We're going to be using those terms too. When is the function increasing and when is the function decreasing? And that just defines the points. If we look at this graph, where is it increasing? Now, don't pay attention to the arrow. That just says that the graph continues. But increasing or decreasing is always talking about if we are moving from left to right. If we start on the farthest left side of a graph and move right, what is going on? So if we start over here and we're going that way, as we do that, this graph is going up. See, the farther we go to the right, the higher that graph goes until it gets to that relative maximum right there. Now, as we continue going right, now the graph's going back down. So this is, I'm marking it with the same color here. This is decreasing to right there. And then once it hits that relative minimum, as we continue going to the right, it will increase all the way as far as the graph goes, all the way to infinity. So this graph here has 2 points where the function is increasing and one interval, the interval between this x and between this x, it's decreasing. So when we talk about those intervals, we're talking about the x values. From negative infinity all the way until it gets to this x value, whatever that x is, it's increasing. And then from that x to that x, it's decreasing. And this x all the way to infinity, it increases. So this asks us to find the turning points of the function. So we're going to graph this function and use our calculator to find the minimum and maximum values. So we're going to graph that in Desmos, since that's what we have available to us here. If you have a calculator and want to do that on your calculator, that's wonderful too. Minus 6x squared plus 7x plus 2. Okay, so this is the graph of our equation. So let's use the calc menu to find the minimum and maximum. Well, fortunately on Desmos, we can just zoom in. If we just click on there, Desmos will tell us the maximum and the minimum. See, as soon as I clicked on that, when it put a point right there, and I can click on that and see what it is. So the relative maximum is 0.7094303. That's the relative maximum. At this point, at this x right here, that is the maximum y. So let me write that down before I go on. So relative maximum at 0.709, that's the x value of that point. And the value of the maximum is 4.303, because that's how high it is. It's 4.303. And then the minimum is right here at 3.291 negative 4.303. Okay. So at 3.291, no, that's not a comma. That should be a period. 3.291 negative 4.303. So here's the relative maximum point. Here's the relative minimum point. Now it wants to know what intervals is it increasing and what intervals is decreasing. Okay, well, let's take a look at that. It is increasing starting at negative infinity. As we go this way, the graph will be getting bigger and bigger and bigger all the way until there. Does that mean there's an increasing interval from negative infinity all the way to 0.709? I'll show you how I wrote that on there. From negative infinity to 0.709, it's increasing. All right. And then from 0.709, from right there, from that x value, all the way until it gets to this x value, it's decreasing. It's going down as we keep going. So our decreasing is 0.709, comma 3.291. So that's a decreasing interval. And then we have another increasing interval from 3.291 to infinity. So I got to add that one. 3.291. All right, I'll show you how I wrote that. So from negative infinity to 0.709, it's increasing. Then it starts increasing again at 3.291 all the way, that's a comma, to infinity. So we put those in parentheses. This interval is in between there from 0.709 till it gets up to 3.291. In that interval, it's decreasing. So it goes up, and it goes down, and it goes up more forever. So that's how we write increasing and decreasing intervals. So on your assignment that you're going to have, let's see, all I have is just more examples there. Let's do this first one together because your assignment will have a few of these type of problems. So we've got to give the domain, the range. Remember, the domain is the x's, the y's are the range, the relative maximum, the relative minimums, in behaviors, increasing and decreasing intervals. So we got a lot to do there. So let's look at the graph of that. Negative x to the third. Oh, we got an x to the third. Let's just make that a negative. Plus 3x squared. All right. So there is our graph. Let's see if I can kind of get both of these on the screen at the same time. And this up here.
Thorax, which is kind of like their head and thorax combined into one, and then an abdomen.
And that. Okay, that kind of gives us both at the same time. All right. So if I click on here, it'll tell me what those values are. Oh, that one's really nice. So the domain, what are the x's that this graph covers? Is there any x that this graph does not use? Because this goes back to negative infinity, and this goes to infinity. Or negative. Well, I mean, the x's go to negative infinity. This goes to infinity. As the x's go to positive infinity, this goes to negative infinity. So the domain is all of it. Negative infinity to infinity. Every possible x is covered. And for the range, up and down, it has no end either. It goes all the way from negative infinity to infinity. So this one's easy for the domain and range. It'll go all the way to infinity every direction. Relative maximum. So we have a relative maximum at 2, 4. Because we can see that. And we have a relative minimum at 0, 0. Now we know it's not the absolute maximum because it goes all the way to infinity. But for this area of the graph, that's the largest point. In this area of the graph, that's the smallest point. End behavior. As x approaches infinity, the function approaches. Let's see, as x goes to infinity, as it goes this way, it's going down to negative infinity. So it approaches negative infinity. And as x approaches negative infinity going this direction, the function's going up. So the function's going to infinity. So the increasing intervals, let me click on these points again. The only place it's increasing is right there. All right, that's it. Between 0 and 2. Between the x value of 0 and the x value of 2, it's going up. So 0 to 2. And the decreasing intervals, it's decreasing from infinity. Well, the x, we'll look at the x, from negative infinity all the way to 0. From negative infinity to 0, it's decreasing. And it's decreasing again once the x gets bigger than 2. When the x is 3, it's back down here, and it keeps going down. So from 2 to infinity, it's decreasing. So this should cover all of our x's. Our x's go from negative infinity to infinity. So from negative infinity to 0, it's decreasing. Then from 0 to 2, it's increasing. And then from 2 on to infinity, it's decreasing again. So that covers all of the x's. So one last sheet. I'm going to skip all these other examples. You guys can do that by graphing that on Desmos. We're going to look at this real quick. Which means I need to bring my camera up so we can see this. Characteristics of a polynomial function. And let's graph that function. Delete x to the third plus 6x squared plus 8x. All right, so that is the graph of this function here on our example. So let's set that over there. There's the top point and the bottom point. And here are where it crosses the x-axis. So turning points. Turning points. That's that maximum and minimum point. See, it turns right there. At that point, it's not going up or down. That's where it turns. So turning points are at negative 3.155, comma 3.079. There's one turning point. The other turning point is negative 0.845, comma negative 3.079. Okay, that's the two turning points. That's all this graph turns is twice. Some graphs turn more, some turn less. Increasing intervals. We'll see it's increasing from negative infinity all the way until it gets to that x right there. So it increases from negative infinity all the way to negative 3.155. And I'll just make a note that these are the x's. These are the x's where it's increasing. And then it starts increasing again once it gets past this point down here. So from negative 0.845 to infinity. It just keeps increasing. So that's the two intervals of increase. The only decreasing interval is in between the two turning points. When x is at negative 3.155 until it gets down to negative 0.845. In between there, the graph is going down. The y values are going down. So again, the domain, all the x's, this goes from negative infinity to infinity. A lot of these do that apparently. And our range for this graph, the range goes from negative infinity to infinity. And you're like, when would it not? Well, let's think about that. If this was if we didn't have this x to the third out front, and it was a parabola, the range would only go from there up, right? There wouldn't be any negative values for this. So the range would not be from negative infinity to infinity. It would be from negative 2.667 to infinity. So we can have, well, there's the x third back in there. Okay. So there can be times where it does not go from negative infinity to infinity. What's the parent function? Well, the parent function is just the x to the third without all these things. You take the largest possible exponent in there and then take away any coefficients. So it's just f of x equals x to the third. If that was 5x to the third, we'd still just say x to the third is the parent function. In behavior, as x approaches infinity, the function approaches what? As it goes to the right, this function goes up. We can see it on the graph. So it approaches infinity. As x approaches negative infinity, so as you start going this way, what's the graph doing? F of x approaches negative infinity. The graph is going down. We can see over in the Desmos, it's going down as we go left. The zeros, that's the only thing we haven't talked about. Where is this graph equal to 0 at? Well, right there. At -4, it's equal to 0. At -2, it's equal to 0. And at 0, it's equal to 0. So the zeros are at -4, -2, and at 0. These are the x's again. What x values is the function actually equal to 0? So we can sketch a graph on here just to have on our notes. I should have went through the 4. Oh. So that's basically what the graph looks like. All right.
So for each segment.
All right. So there is the last page of the notes. Get past that, we just got blank paper. So that gives you basically everything you need to know for this week's assignment. Our assignment is loaded in formative. Let's go look at that real quick. Formative. Yes, I'm leaving you, Desmos. Goodbye. Arrivederci. We'll see you another day. Okay, so this is what it'll look like.
Yeah, anyway, so you can just go through
Key features of polynomials. So your first problem, you've got 4 questions for the first problem. And it's basically this. The end behaviors, 1, 2. Is it even or odd? Is this an even or odd function? And what is the sign of the leading coefficient? Is it positive or negative? You can click on this if you need a better look at it, and it'll bring it up full screen for you. Right? So you can see. But the problem's over here on the right. End behavior. As x approaches infinity, what is fx doing? Is it approaching infinity? Is it approaching negative infinity? Is it approaching 0? Is it approaching -7.8? As x approaches negative infinity, what is the function doing? I was nice and I made all these multiple choice. I started to make them where you had to type in the answers, but I made these multiple choice. Is this an even or odd degree function? Is the sign of the leading coefficient positive or negative? Okay, then you got another one down here. Same questions. As x approaches infinity, which way is this graph going as it approaches negative infinity? What's it approaching? Is it even or odd, or what's the sign of the leading coefficient? Okay, then you have 2 questions right here. Describe the end behavior of a 14th degree polynomial with a positive leading coefficient. Well, that's what a little cheat sheet helps. Oh, it's 14th degree. Is that even or odd? And it says it's a positive leading coefficient. So you should know. The left is down, the right is down, or the left is up and the right is down, or they're both up, both degrees pointing up, or both pointing down. Just whatever your little cheat sheet tells you that. Then you've got, I think I've got 3 problems that are all like this. Let's zoom in on it. I give you the graph. I give you these points that Desmos gave us. I ask you, what's the domain, the range? It's just like the last problem we just did together. What's the domain? What's the range? What's the relative maximum? If there's more than one, there may be more than one. Relative minimum, maybe more than one. Doesn't look like it on this graph. And then the end behaviors, 15 and 16. And then the increasing intervals and decreasing intervals. Where's this graph increasing? There may be just one interval. There may be multiple intervals where it's increasing or decreasing. So you fill all those in. These you do have to type in, because what's the domain? What's the range? When you type it, it'll take you to the math input, though. If you're typing infinity, you'll see an infinity symbol right there. So here's the infinity button right here on the right. So anytime you want to use infinity, it does have an infinity button. You just have to click on that little infinity symbol right there. And it'll take you to this symbol menu where it has infinity right there. See, so you can type infinity. That is available. All right. So you have that. Then you have one that looks like this. And then, see, that one may have, that looks like, if we zoom in on this, this has more than one relative minimum. That's a relative minimum. That's a relative minimum. That's a relative maximum. This is the point for that right there. That's the coordinates of this black point. So we have the same ones. And then the last one we have is this graph here. And it's a 2x to the third minus 7. And you're welcome to graph these on Desmos if you want to. If you can't see that well enough, or you want to get more information that I haven't highlighted, here's the equation right here at the top. You can put that in Desmos, and then you can click on the graph, and it'll tell you all these points. So that's available for you. But that is it. That is the end of the assignment. There it is. Key features of polynomials. We're going to continue with this over the next few weeks and dig deeper and deeper, but this is our start. So work on turning points, domain and range, increasing, decreasing intervals in behaviors. And if you got any questions, I'm happy to help you with that. Otherwise, I'll let you go ahead. Have a great week back to school, and we will see you Wednesday. This is a B week for Friday. It's a slant B week for Friday. So Wednesday it is.